Hi there, so welcome to the third video on pitch stability. Now the previous two should be in the links below, so if you've not already seen those, good place to start. In those ones we talked about generally how pitch stability is achieved in general for aircraft, and then in the second one I talked in a bit more detail about how it worked for hang gliders and flying wing tailless aircraft. Now what we're going to come on to in this one is a bit more specific to, almost specific to hang gliders. So we're going to talk about tucking and tumbling. That's something that, although it is possible for other types of aircraft, they can happen. It's particularly an issue for hang gliders on account that they're tailless aircraft, they're weight shift controlled, they're pretty lightweight aircraft that are often flown in pretty strong conditions. So those factors together mean that tucking and tumbling is much more of an issue for a hang glider than it is for most types of aircraft. So to understand tumbling, we've got to think in terms of the dynamic response of the hang glider. So far, the previous two videos, they were all talking about static stability. Now what we mean by that is that you can sort of almost imagine this as being a bit analogous to like a spring. So if the hang glider changes its angle relative to the angle it wants to be flying at, it's like squeezing a spring, and that spring tries to return it back to its normal position. So the further away you get from its normal flying angle, the more force there is trying to push it back towards its normal flying angle, whether that's the nose goes too low and the thing that's acting like a spring is trying to push it back up, or the nose goes too high and it's trying to pull it back down again. Now, although we talk about this as static stability, it's important to realise that it's not really a spring, of course. What's actually happening is it's those aerodynamic effects that we talked about in the last two videos. So those do rely on airflow over the wings. So the wing needs to be flying forwards. It needs to have airflow for those mechanisms to happen, for those springs, if you like, to actually exist. Now the other thing that's really important to bear in mind throughout this is that hang gliders are weight shift control aircraft. You control them by shifting weight. Now obviously we do that by pulling and pushing on the control bar, and we move our centre of mass forwards and backwards. Now in normal everyday life, mass and weight pretty much mean the same thing. But in terms of flying, it's only when the aircraft's under normal positive g-force that by moving your centre of mass forwards and backwards, you're also shifting the weight and forwards and backwards. So that means you only have control when you have weight on the glider. In other words, when the glider has a positive angle of attack and it's generating lift. So let's think about the details of how weight shift control works in normal flight. So let's say we pull the bar in, so we're moving our mass forwards, we're moving the weight forwards, we're considering moments around the centre of mass. So that means that although the centre of mass has moved, we can kind of think of it as it's like the lift has moved backwards. So the lift is being generated behind the centre of mass because we moved the centre of mass forwards. Now obviously that creates a nose down pitching moment. Now because with the static stability in the wing that we talked about in the previous videos, then that means that the wing compensates for that. The lift will move forwards on the wing and it will balance out again, and we'll just trim at a higher speed. If we push our weight and our mass backwards, now the lift is being generated in front of the centre of mass, which then means it pitches up, and then those stability factors all kick in, and again the lift is redistributed, the forces line up again, and we stabilise at a different speed. But let's just think for a moment what would happen if we were momentarily weightless. So you get one of those straps loose moments because you've hit really strong turbulence, for example, and that means at that moment the wing is at zero angle of attack. Well, it's at zero lift, it's generating zero lift, and that means that you have no weight now. Effectively at that moment it's you're in free fall, so there is no weight to be shifted. So moving your centre of mass forwards and backwards by pulling in or pushing out, that's not really changing very much because there's no lift, so that there's no lift moving relative to your centre of mass, so that means there's no stability. Now there's a few different cases we can consider of what might happen at this moment. So let's consider the first case is the one we want to happen. Now in this case we're flying forwards, we've got plenty of airspeed, and we're also flying a glider that has the stability built into it that we've talked about in those previous videos. So the washout rods, the luff lines, the twists, the washout, the some reflex maybe, all of those mechanisms which contribute to positive stability. So if that's the case and you have airflow over the wings, forwards airflow, you're still flying forwards, then those stability devices all kick in and they act to pitch the nose of the glider up. It starts generating lift, the weight comes back on it, and normal service is resumed. You fly away from it. However, there could be another case. So in this case, let's say we are still flying forwards, but the glider isn't correct. So for whatever reason, maybe the sprogs have been set too low on it, so it doesn't have that stability margin. Or maybe it was one of these really early designs of gliders from the 1970s which could do bad things when they were unloaded. Now in that case the glider won't recover itself, and in that case the glider will carry on diving, and that's going into a tuck situation then. Now there's a third possibility as well. So in this possibility, let's say you are actually flying a safe glider, so one that is pitch stable, it's got that static stability that we talked about in the previous videos, but in this situation it's flying extremely slowly, so say basically close to zero airspeed. Now in that situation there is none of those mechanisms that we talked about previously are directly effective. So the twist, the reflex, they're not going to do very much because there's no airflow over the wing. So in that analogy with the springs, basically you don't have any strength in those springs to pull the nose up or down to correct it. So in that situation what really takes over is momentum. So this is why we're talking about a dynamic response, because it's to do with motion. So if in this situation, as is quite likely, the glider is starting to go over nose forwards, then it has a certain amount of inertia, it has a certain amount of momentum, which is going to try and keep it going, which is then when we get into what we talk about as a tumble. Now obviously these are situations that we really want to prevent, because at this stage it's very unlikely that the glider's going to recover, so it's effectively it's time to throw the reserve at that point. So how do we stop this from happening? So we can view it from two ways. We can view it from the design point of view, we can view it from the pilotage point of view. So thinking about it from a glider design point of view to start with, so the first thing to say is that obviously you need to have static stability. So what we discussed in the previous video, so sweep, washout, reflex, you need to make sure that if the nose goes down, there's aerodynamic forces that are trying to push it back up as long as the air's flowing over the wing. So that's why we do the pitch testing on the test rig, because that's a way of checking that those devices are functioning in that way. So it's obviously very difficult to get it to a 0-degree angle of attack with forward speed over it. It's not really something you can do in normal test flying. The only way you can do that is by putting it on a test rig and winding down the angle of attack to 0 and below 0, and making sure that even at those negative angles of attack, that your luff lines or your sprogs are working and are trying to restore the glider to back to nose up. So that's how in glider design you can prevent that first type, the sort of tuck type, from happening. But there's the second type, which is when you're flying extremely slowly. You have basically no airflow over the wing at that point. So none of those devices will work. The twist, the washout, the reflexes, in the way that we were talking about, they don't have that effect because they don't have airflow. If there's no airflow over the wings, they can't function. So in that situation, as I say, it's the momentum and it's the resistance to the rate of change of pitch. So you've got the pitch angle, but then you've got the speed at which you're pitching forwards. Now, there's also something which can resist that, and that's what we talk about as damping. So damping, you might have heard of that term in reference, it's quite commonly you think of it in terms of something which is oscillating. So like on your cars, you have suspension, you have your springs, but if you didn't have anything apart from the springs, then the car would bounce up and down on the road. So what it also has is dampers, sometimes incorrectly called shock absorbers, but they're there to prevent those oscillations. And the way that they do that is by acting against speed of movement. So in the case of the glider that's just on the point of going towards a tumble, it's rotating forwards, so you've got momentum there that's making it rotate forwards, but then the faster it rotates, it's rotating through the air. So even if it's not going forwards through the air, because effectively it's trying to spin around its axis through the air, it's the damping factor which resists the speed, how fast it will rotate. And of course, if it rotates fast, then it's probably going to carry on into that tumble and go end over end. But if there's something which slows that rotation speed down, so it only rotates slowly, then of course it will get towards a steep dive, a vertical dive, but as long as it doesn't rotate any further than that, then it can start to gain airflow, gain speed, because it's in a dive, it's going downwards. So once that airflow is re-established, then as long as you have that static stability, then those other stability devices all start to work and it will fly out of the dive. So you can see that it's really important that you also have a damping effect on the pitch as well. So this is something which has been simulated and modelled quite a few times over the years, actually, and again, it is this damping factor which seems a very significant factor in whether the tumble will happen or not. So what can we do to increase the damping? Well, if you remember back to the static stability we were talking about, so the way you get the static stability, you have to have centre of gravity far forwards, and to stop that forward centre of gravity just causing the thing to dive, then you need to have a stabilising surface which is set at a lower angle of attack than the main lifting surface. So that's what we call the longitudinal dihedral between the lifting surface and the stabilising surface, or the front surface and the back surface. So if you want to achieve a certain amount of sort of nose up pitch, which is what you need to do to counteract the forward centre of gravity, then you can either do that by having a relatively small surface close to the main wing, but angled really steeply, or you can have a bigger surface further away and angled a lot less steeply. They can both create the same amount of nose up pitch. So they could give the same level of static stability, but they'll give different amounts of dynamic stability. So if you have the big area and further back, even if it's not set at a very steep angle compared to the main surface, it will act as a very effective damper, because you've got a lot of sort of area that's been trying to be pushed flat through the air. So that can help with this resisting the rate of rotation. Now, one way you can put that area on a long way away from the main lifting surface is that you can have a tail. So tails quite often come up in these kind of discussions, and that's a perfectly valid, that's a good way of doing it. But you can also look at where the area is on the wing as well, because even with a tailless wing, there can be a difference in where you put the area with how much damping effects and how much dynamic stability it's going to give you. So if you have because on our swept flying wing, we're effectively using the outer bit of the wings, because it sweeps back, those are the bits which are furthest backwards, then they're acting as our stabilising surface. So if we have a wing that has a lot of twist on it and is pretty sharply tapered, like most current hang glider wings are, then that's giving you all of the static stability you need, but because the wing's quite tapered, you've not got that much area that's far back, so it's not doing such a good job of reacting against the rate of change of movement, so it acting as a damper. So this is basically like having the small stabilising surface but with lots of angle on it, and that's what we've got on most current gliders. So then you can see why adding a tail helps in that situation, because it's adding more area. But there's another way you can think about this as well, because you can have more area further back by making the wing wider towards the tips. So by having a less tapered wing, that also gives you the area, and then you don't need to have so much angle on it because you've got more area, so you have less twist. So you can also achieve that damping effect through that route as well. But doing it that way also does have a benefit in terms of performance, which we can come on to in a future video. You also see with hang gliders that do use tails that they're not massive and they can't be that far back, because there's a limit to how long you can make the keel before it would start to get in the way when you're flaring to land. So that means that if you actually consider the amount of area that you've got in one of these tail planes and how far back it is relative to the main lifting area of the wing, if you were to put that area to the wingtips instead, it's not actually that massive. You're not making an enormous change to the so you can get the same amount of stability that the tail would give you, but get it from plan form instead. Now, there's to get the performance advantage I just mentioned for that, there's actually quite a bit of complexity to that, and yeah, that's completely a subject for another video, so we'll come to that another time. I also said we'd talk about what you can do from a pilotage point of view to reduce the risk of a tumble. So the first thing is on the glider settings. So as we saw earlier, you need to have static stability. If you don't have static stability, then there's this potential for going into a tuck, which can then develop into a tumble. So that means that basically don't lower the sprogs too far. That's the first thing. And check sprog heights, check luff line lengths. They've all got to be within the level that's been pitch tested and passed on the test rig. So assuming that's done, and assuming the glider does have high enough sprogs that it is actually pitch stable, then the next thing is, well, what situations in the air can lead to a tumble? So for a tumble to happen on a glider that actually is set up correctly, there needs to be two things present. So it needs to be at very low airspeed, so that you're not having the airflow over the wings that would normally provide that stability, and it needs to be at a negative angle of attack, or to be dropping the nose in the process of rotating downwards. So the first situation you can see that could happen in is with aerobatics, and particularly failed attempts at aerobatics. So if the glider ends up in a very, very steep climb, for example, for example, trying to do a loop and not making it all the way, then you can see that basically it's going to stop and rotate forwards, and that's a way that a tumble can occur. So that's why we don't really recommend doing aerobatics on hang gliders, or at least not until you've built up an enormous amount of experience, you really know what you're doing, and you've got things dialed in so that you're not going to be in this situation of ending up half doing a loop. But the other situation is, it comes about from the fact that we're generally flying these aircraft on days and in conditions when the air is quite strong. I mean, that's what we're looking for. We're looking for strong thermals so that we can fly the big distances, get the good lift. And hang gliders are lightweight aircraft. They are affected by turbulence. So when you fly into very strong turbulence, that can also put the glider into these situations where a tumble can happen, and they do sometimes happen in situations where realistically there's very little the pilot could have done to have avoided it. There are still a few things though to look out for, and a few things to at least reduce the chances of it, to make it less likely. So the biggest one is just choosing where you fly. So the obvious case is, I mean, there's lots of other sources on this. All the books explain these sorts of factors, so I'm not going to go into them in great detail. But the obvious ones are lee side of mountain. So if there's a wind, if you're downwind at the mountain and not massively high above it, there's a very good chance that there's going to be some form of rotor there. There's going to be strong turbulence. So bearing in mind that the sort of the worst case for the glider to hit turbulence, because bear in mind the turbulence, it can be gusts in a vertical or in a horizontal direction. So the very worst case you could have would be a downwards gust, but that's also coming from behind, because that's doing the two things at once. That's putting the glider into this negative G situation as the downdraft hits it, but it's also robbing you of airspeed, because if there's a horizontal component to the wind as well, then it's coming from behind, then it's stealing some of that airspeed from you as well. So that's putting you into this really, really bad situation. So yeah, as I say, behind obstructions is where that sort of, especially behind mountains, is where those sorts of situations could occur. Also dust devils, so a really, really powerful thermal very close to the ground. It's got to ring warning bells that it might be a dust devil in there, and so there you can have very strong upwards flow of air, and next to it you can have very, very strong downwards flow of air, and also with horizontal component because it's going round and round. So then again, you've got this situation where you could fly into a situation where you're being exposed to negative G and hit by a gust from behind all at the same time, and then that's a really risky situation to be in. If you do find yourself in really violent air though, then a good tip is to fly a bit faster. So because, as I said earlier, one of the risk factors in causing a tumble is your airspeed suddenly dropping because you've been hit by a horizontal gust of wind, which has robbed you of your airspeed. So if you have a little bit more airspeed to start with, then it has less effect, having been hit by the same strength gust. So it gives you more safety margin. So flying a little bit faster through the rough air, it doesn't mean stuffing the bar to your knees and absolutely tanking it. It just means adding a few extra miles an hour, pulling the bar in a little bit, just getting a little bit more speed on it, but not doing that by pulling the VG on. So leaving the VG quite loose so that you've got a lot of natural pitch stability in the glider from the wing being twisted, but pulling the speed with the VG relatively loose. And the final thing that you can do is, just in that moment, if you start to feel like the glider is tipping, is going, then there's one thing that's really important not to do, and that's do not push out in that situation. Because although it feels very instinctive, very natural, that it feels like the glider's diving, you want to push out to recover it from it, what you're doing is actually having the opposite effect to what you want. So you're moving your centre of gravity backwards. Now, as we saw earlier, in normal flight, you've got weight on the glider, so you're shifting your weight backwards by pushing out, and so that will raise the nose of the glider because you're moving the weight behind the lift of the wing. If you're in a 0G situation, then moving your weight forwards and backwards isn't going to have any effect. Well, you don't have any weight to move forwards and backwards. You're at 0G. It's even worse if it's a negative G situation. Now, just ignore for a moment the fact that actually you're hanging from the glider. So if you're at negative G, you're not hanging anymore. You're actually being lifted up and pushed against the glider. But if you were able to move your weight in that situation, then pushing your weight backwards is having exactly the opposite effect, because now effectively your weight is acting upwards and the lift on the glider is acting downwards. So that means that having the weight further backwards is just enhancing that nose down movement. Now, in practice, you are hanging beneath the glider. You've got a flexible strap that you're hanging from. So what would tend to happen in practice is if you were to push out at the wrong moment there, makes it much more likely that if you do hit the glider, you're going to hit the glider far back. Probably your feet are going to hit the keel or the trailing edge of the sail, which is just going to tip it the rest of the way. And if you watch some of the videos, there are some videos on YouTube where you can see tumbles. You can sometimes see this happen of the pilot's feet hitting the glider, and that's often the final thing which tips it over into from what maybe might have recovered to something which definitely won't recover at that point. So avoiding the temptation to push out because the nose drops is important. So if you imagine what you could do instead, if you're able to really pull in and get yourself as tight onto the bar as you can. So I've never done aerobatics, but I've heard from the people that do that they often favour the more flexible harnesses, and one reason is because they can get more weight forwards, and partly that's to get more speed for entering the manoeuvres, but also it's because if it does go wrong, they've described sort of wrapping themselves around the base bar, trying to really like curl up and grab themselves onto the base bar, because if their weight is staying on the base bar, is staying far forwards, it stops their feet from hitting the sail. And if you keep the weight on the front of the glider, it's actually quite a good chance that it will recover itself. Effectively, it's going to come out, it's going to recover into a steep dive, and then of course once you're in that steep dive, the glider is now flying again. The normal stability mechanisms are going to take over and are going to start to try to raise the nose. Now in that situation again, you need to manage the energy and not just come straight out of one situation and into a very nose high into another problem. But that's the best bet is, if you're in the situation where the nose starts to drop and you feel like it's starting to tip, resist the urge to push out, absolutely. And if you're able to, grip the base bar and pull yourself against it and avoid yourself getting pushed up against the glider. In all honesty, these are such dynamic situations. The good news is it's very rare that this happens on hang gliders, and you need to be in really pretty violent air for this to happen. And in that situation, there's no real certainty over what's going to occur, because as I say, these are lightweight aircraft being flown in conditions that are extremely strong. You can't necessarily predict the outcome, but you'll give yourself the best possible chances if, first of all, you avoid those conditions. Secondly, you're flying with a little bit more speed. Thirdly, you have the VG set loose, so you're maximising the natural stability of the glider. And finally, if it does go wrong, you try and get your weight forwards and absolutely prevent your weight from going backwards. So that wraps up for today. As I say, tumbles are very rare. I mean, personally, I've never experienced one. To be honest, I don't think I've ever really been that close. I've had moments where I've gone momentarily weightless, where the straps have gone loose and the sort of wires have twanged, and moments where you've sort of felt like you're dropping a little bit, but it's never actually felt like it's really getting close to that. So, and I have flown in fairly strong air as well, so it's an unusual thing to happen. But as you can see, there are at least some things, well, there's certainly things we can do from the glider design point of view that we do that minimise the risk. There's also things as a pilot you can do to reduce the risks as well. Certainly if anyone has actually experienced this for real themselves, it'd be interesting to write your experiences in the comments below. I think for the next video I'm going to do a bit more, wrap up the stability theme by talking about roll and yaw stability, because so far we've only talked about pitch and we've not talked about the other axes. So yeah, I will do another video on that. Just as a reminder, I've also got the Patreon page going, which is trying to put some of these ideas that we've got on hang glider development, and we're now actually starting to build these into a prototype. Ow.